Okay, now let's look at exercise 5. This one is exercise 5. Okay, so the location of the sliding bar is given by the x equals to 0.2t. So x is actually the position. If you look at this diagram, okay, this one is the axis x, this is axis y, and also axis z. So you have a sliding bar here. So the sliding bar will locate at different value of x at different t. Okay, different time it will be located at different position x. And the separation of the two rails is 20 centimeters. Separation between the two rails, which means the distance between the A and B is 20 centimeter. So given the B is this one, okay, and you have to predict the voltmeter reading at the position x equals to 100 centimeter. Okay, so let's look at the solution. So you can draw this diagram, okay, in your own drawing. Okay, so this is my drawing. So I draw it in 2D instead of 3D. Okay, so this is x-axis, y-axis. So I have a separation of 20 centimeter, and this is the moving bar. Okay, moving bar. And according to the information from questions, okay, the B is equivalent to this one. Okay, so I have to refer to the direction of the axis. Okay, so this is y direction, x direction, and I define myself the z direction. The positive z direction will be pointing out from the page. Okay, like this one. This is a positive z. So I draw this magnetic flux density. Okay, here. Okay, to represent the direction is positive z. Okay, so if you refer to this equation, you will find that it doesn't contain any t, which means that this b is a fixed value. And if you refer to the questions here, okay, the bar is moving, okay, because the v is given. So when the bar is moving, okay, it is motional EMF because it's moving. You have velocity, and this is the position of the sliding bar at different time. Okay, and you have to find the voltage, EMF voltage at 100 centimeter. So since it has a velocity, it is motional EMF, and we have to use this one. Okay, so this is the equation for motional EMF. And if you look at all the symbol here, this is the velocity, it has direction. And for the magnetic flux density, it has direction also. And for the dl, okay, the length, okay, it has direction also. Okay, so the velocity is not given in the question, but they give us the distance. Okay, the distance, how far it moves, the distance, the location. So based on the simple equation here, the velocity is defined by you divide the distance with time. Okay, so the distance is given, which is 0.2t. When you divide it by t, so it will be 0.2. So this 0.2 is the velocity. Okay, we refer back again to our questions. Okay, so the sliding bar is moving in this way. Okay, so it is moving in the positive x direction. That's why this one is a positive x. So now I replace this velocity here. Okay, this is the magnitude, this is the direction, and the b, this one is the b. Okay, and this is the direction. And now dl, I put it here. So this dl, okay, is depend on the direction of current flow. Okay, so we have to check back our loop, okay, our sliding bar. Okay, so this is the original magnetic flux direction, positive z. And according to the Lenz law, the generated current, the red one, okay, must produce another magnetic field which opposes the direction of the original magnetic field. Okay, so I must produce this one. So if you use your right hand rules, and these two represent the direction of the magnetic field, okay, or the direction of your four fingers, this will be the direction of your current. So your current is flowing in the negative y direction. So the dl here will be represented by dy and current flow in the negative y direction. So you have a negative y here. Okay, so you replace this dl with this one. Okay, and next one will be the interval for your l. Okay, for your dy. Since the current is flowing in this way, you have to integrate by using the other direction, which is from point B to point A. So point B is 0 position and point A is 20 cm position. So it will be from 0 up to 20 centimeter. So for 20 centimeter, you have to convert it to meter, which will be 0.2. Okay, and for this one, you need to perform the cross product. Okay, so for the magnitude, you just multiply like usual. Okay, and for the cross product between the x and z, you have to use this method. So x, y, z is here. Okay, if x cross product with z, we look at here, x cross product with z, we are in the reverse direction, so the resultant direction will be negative y. Okay, negative y, and when this negative y dot product with the negative y here, you will get 1. Okay, we will get 1. So the integral will become something like this. Integral will become something like this. So this is x, not y, so it will just remain. Okay, so after you integrate, you will get another 0.2 here, and the equation for the motional EMF will be this one. And when you want to find the value of the motional EMF when the x is 100 cm or 1 meter, okay, you can just replace the value into the equation, then you will get the generated motional EMF equivalence to 0.016. Okay, so this one will be, okay, the answer is given here. So this one will be question 5.